The first two-thirds of this course, we're going to be using my book, Solving Partial Differential Equation Applications with PD2D, to derive and solve a wide range of partial differential equation applications. For example, some ordinary differential equations, modeling a damp spring and pendulum in Chapter 1, plate and beam bending problems, those are 1 and 2 dimensional problems, diffusion and heat conduction, including some application to image processing. Chapter 4, some interesting applications to pricing options, financial markets. Then elasticity, stress and strain problems in Chapter 5, fluid flow, then Schrodinger and eigenvalue problems, minimal surface membrane wave problems. But the emphasis is we're going to be using the program PD2D, which I've developed over about 45-year period to solve these applications, but the focus is not on PD2D. The focus is on the applications. We'll be deriving them and solving them and determining what types of boundary conditions and initial conditions go with what partial differential equations, partial differential equations model what situations, and so forth. So it's all about the applications. Not the software is just a tool to see how these applications work. So even though we'll use PD2D extensively in the first two-thirds of the course, the focus is really on the applications themselves. We'll be deriving some of the partial differential equations and we'll be solving them just to see what solutions look like and how they depend on boundary conditions and what boundary conditions, initial conditions are appropriate for which problems and so forth. Nevertheless, we need to learn a little bit about PD2D in order to use it. So the chapter I, which is basically chapter 0 of the book, goes into some detail about using PD2D. So that's what this first video is about. Despite the name, PD2D actually solves 0D, 1D, 2D, and 3D problems. Originally only solved 2D problems, but now it solves three-dimensional problems. And it uses finite element methods, but it uses two very different brands of finite elements, the Galerkin and the collocation methods, and it's the details of how these two versions work are in the appendices, but we're not even going to look at that. I just want to give you enough information so that you can decide which method you need to use for which problem. So let's look at the differences as far as the user is concerned between the Galerkin and collocation methods. In fact, this course is really not about numerical methods for solving partial differential equations either. That's a different course, 5343. Here we're just going to tell you enough about the methods so that you'll know how to use them. And as I said, there are two basic brands of the finite element method that are used by PD2D, collocation and Galerkin. Galerkin is the one that most finite element programs use. It's very rare the use of the collocation method, but PD2D uses it extensively. Most of the time when people are talking about the finite element method, they mean the Galerkin finite element method. And what are the differences? Well, first of all, for 0D problems, and the dimension of a problem is the number of space variables, not counting time. So 0D means ordinary differential equations are actually steady state. 0D problems would just be a system of linear and nonlinear equations. Time-dependent 0D problems would be a system of ordinary differential equations. And that doesn't really use finite element method at all. So this is the difference between collocation and Galerkin are irrelevant for 0D problems. They're also irrelevant for 3D problems because PD2D only has collocation for 3D problems. There certainly could have had a Galerkin solver for 3D problems. A lot of software does, but PD2D only has collocation methods for the 3D problems. So the choice between collocation and Galerkin is only relevant for 1D and 2D problems. And there are basically two major differences between the methods as far as the user is concerned. And one is the form of the differential equations. The Galerkin method has this divergence form, which is the partial with respect to x of something, which can involve first derivatives, plus partial with respect to y of something, which can involve first derivatives. So overall, the left-hand side here is generally second order, but it has to be in this divergence form, the divergence of the vector AB, where A and B are can be functions of the unknowns and their first derivatives. So you get a system of second order equations here, and then it's equal to F. And that's kind of a strange, first it seems like a strange format for the partial differential equation. The collocation equations are seemingly more natural. Here are the collocation format for partial differential equations in 1D, 2D, or 3D. And basically they're just the most natural looking. You just put everything on one side, leave 0 on the other, and the left-hand side is your F1, F2, and so forth. And that can involve second derivatives. So both collocation and Galerkin solve second order partial differential equations, but the Galerkin method requires you to put it in this divergence form. The collocation method allows you to write it in what seems like a more natural form. And boundary conditions are especially seem to be more natural for collocation. Again, the boundary conditions involve first derivatives. You just take everything on one side and call that G1 and so forth. And so, they're simpler setup, the partial differential equations and boundary conditions for collocation method. The Galerkin method has this strange divergence form, which, by the way, is not a feature of PD2D. It's a feature of the Galerkin method. Everybody that uses Galerkin method, which is most finite element programs, are required to have that format, that divergence format. But the boundary conditions are particularly seemingly unnatural for the Galerkin method. They have to be, remember A and B are the two components of the vector. They can be functions of the first derivatives, vector AB, and that's dotted with the unit outward normal is equal to GB1. So that seems like kind of an unnatural way, and it is kind of a pain in the neck for some problems. But the Galerkin method is actually more natural than collocation for many applications, as we'll see. You'll be surprised to find that it's actually easier to set up the Galerkin PDEs and even the boundary conditions for certain applications. They're actually more natural, surprisingly, than collocation, but collocation method at least seems to be more natural. And so these differences apply to, I've written them for 2D problems, but for 1D problems, the same thing. Have to have this divergence form for Galerkin, and you don't have to for the collocation. You have to have this funny form for the boundary conditions that you don't for collocation in 1D or 2D problems. So that's the first main difference as far as the user is concerned between Galerkin and collocation. Which format is easier to put your partial differential equations and boundary conditions into? And you might think the answer would normally be collocation, but sometimes it's not. The other main difference between the collocation and Galerkin method is the way two-dimensional regions are handled. So this is not relevant for 1D problems because they both just handle intervals A to B. And it's not relevant for 3D problems because there is no Galerkin option. So this is strictly a 2D issue. And the Galerkin method can be used to handle completely general 2D regions. For example, here's Venezuela region, complicated region, curved boundary and all. This can only be handled by the Galerkin method, which divides the region into triangles and automatically refines the triangulation. You could certainly not handle a region like Venezuela using the collocation method. So if you have a complicated region, then you're going to have to use Galerkin method. Collocation method handles, I say, a wide range of simple regions in 2D or 3D. Basically what that means is that your region has to be possible to put it in to parameterized form with constant limits on the parameters. For example, this torus here can be handled by the collocation method because you can write x, y, and z for this torus as a function of parameters p1, p2, p3. Here p1 is the toroidal major angle, p2 is the poloidal minor angle, and p3 is the distance from center line. And if you can write your 3D region, or that's the 3D torus, or 2D region, which is, here's an example of a 2D region, namely this region. If you can write your 3D or 2D region as x, y, z, or x, y in the 2D case as function of parameters with constant limits on the parameters, then you can solve it using the collocation method. Otherwise, you can't. So you can solve regions like this. This is parameterized, for example, using this parameterization. X is simply p1, y is p2 times 1 plus p1 square, where p1 goes from minus 1 to 1, and actually so does p2. So they have to be constant limits. So this is a wide range of simple 2D and 3D regions. You certainly can't write a complicated region like Venezuela as in this parameterized form with constant limits on the parameter. So you can handle a wide range of regions in 2D and 3D using collocation, but a complicated region, arbitrary boundaries, has to be Galerkin method, which is why Galerkin method's a lot more widely used, I suppose. In fact, the collocation method used by PD2D is actually rather unique. The Galerkin method is pretty much standard triangular elements of up to 4th degree. The collocation method is pretty much unique. The way it's used to handle more general regions is a PD2D invention, but it is sometimes better to put it in, even if you could use either method. Some problems are a lot easier to set up as a collocation problem because of the format of the partial differential equations. So, for example, in 3D, you could use cylindrical or spherical coordinates with constant limits on the spherical or cylindrical coordinates. Toroidal, here's a region we just discussed where you have constant limits on the parameters, so you can handle that using collocation. Now, the Galerkin method is handles more general regions, but it's a little harder to not only to set up the partial differential equations, sometimes it's not, but defining the region is more complicated usually for Galerkin method because you have to supply an initial triangulation. Collocation method is pretty easy to set up the method. So basically collocation is usually easier to use than Galerkin, so if you can use it, it's probably better. But Galerkin will handle more general regions in 2 dimensions. 1 dimension, they're all the same. Now, I said the Galerkin method, it's a little harder to set up the region. For example, let's suppose that you wanted to solve the problem in the same region we just showed that collocation method parameterizes. if you want to solve using the Galerkin method? Well, normally you have to define an initial triangulation, which is basically consists of a minimum number of triangles necessary to define the region. In this case, it looks like 8 triangles. You have to supply the vertices and the boundary curves and so forth. So it's a little bit of a pain in the neck. However, even for the Galerkin method, if your region is simple enough to be written as x and y functions of p1 and p2 with constant limits on p1, p2. In other words, if your region is simple enough to be solved by the collocation method, then it's actually easy to set up the initial triangulation. So the Galerkin method allows 2 options for the initial triangulation. If you have a simple region that can be parameterized, in other words, basically the same set of simple regions that collocation can solve, then you can set up your initial triangulation sort of automatically. You define the parameterization and it will automatically set up your initial triangulation. Otherwise, for a more complicated region, you've got to do it by hand. And in either case, PD2D will automatically refine the triangulation. So the more triangles, the better. The triangles, basically, you're approximating the solution by piecewise polynomials that are different polynomials on each triangle. And so the more triangles you have, the more accuracy you'll normally get. And the initial triangulation is basically just to get you started, minimum to get you started. Then you say, well, I want 1,000,000 triangles, and you can even say I want it most dense in this area because the solution is changing most rapidly here, and it will automatically refine that, so you don't have to worry about the final triangulation, just the initial triangulation. Okay, section 2 is about the PD2D user interfaces, and the main PD2D video goes into some more detail, showing an example using the GUI, the graphical user interface, and the interactive driver, which are your 2 interfaces. And future videos and the later chapters will go through several of each, GUI and the interactive driver. Basically, the GUI is easier to use, but is more limited as to what type of problems you can solve. In particular, the GUI is will only give you access to the collocation methods. And here's an example. The first couple of pages of the GUI, it asks you what's the dimension of your problem, is it steady state, time dependent, or eigenvalue, how many partial differential equations, and so forth. And then there'll be 10 or 15 pages where you supply information. It's relatively easy to use, but only for the collocation method. So you'll have to define your x and y, or x, y, and z in terms of the parameters and give the limits on the parameters and so forth. The reason it doesn't access the Galerkin methods is I didn't think that it would really be that useful, because the Galerkin method's going to be a good bit harder to set up even with a GUI. So basically I say that the GUI, the graphical user interface, makes easy problems really easy. But if you have a hard problem, you're probably going to have to use the interactive driver. So the first few examples we'll do in this book will be using the GUI. So that's the GUI. It's easy to use. It chooses a lot of defaults for you. It won't ask you a lot of questions. It'll choose defaults for you. Then there's the interactive driver interface. And again, the main PD2D video goes through an example of each. But here's one section of the interactive driver interface. It just starts asking you questions, but it'll ask you a lot more questions than the GUI does and give you more flexibility. You'll have to make more decisions, and it's the only way you can access the Galerkin methods. It's also the only way you can solve more than 8 partial differential equations, and the GUI has some other limitations. But as I said, the GUI is basically for easy problems, and it makes them extremely easy. The interactive driver is for everything else. The interactive driver, you don't even need to have the GUI. As a matter of fact, a lot of people don't even bother installing it, because any problem you can solve with PD2D, you can solve using the interactive driver. In fact, the GUI is really just a front end for the interactive driver. It takes all the answers that you give the GUI and sets up input to the interactive driver. So by definition, anything you can solve with the GUI, you can solve with the interactive driver. The GUI makes them easier, but the interactive driver gives you more flexibility, and it just starts asking questions, and you input yes or no, and the coefficients. For example, here's your. You said you wanted to solve a system of two second order, two 2D problems. And it says, well, here's the format, what's F1, what's A1, what's B1. Notice the divergence form. The derivative with respect to x of A1 plus derivative with respect to y B1 equals F1. A1, B1, and F1 can be functions of x, y, and the solution in the first derivative. So basically, even though it looks like first derivatives only over here, A1 and B1 have first derivatives in them, so it's really second derivatives, but it has to be in this special divergence form. Sometimes it requires some work to put it into that form. Sometimes impossible. On the other hand, the collocation method, sometimes hard to put it into that form, sometimes impossible. So this is a typical interactive driver session. It's more work, you have to answer more questions, but in either case, the result of either the GUI or the interactive driver is it will produce a Fortran program. And here's a portion of that Fortran program. It's all written for you automatically, just taking the answers that you gave either the GUI or the interactive driver and sticking them in the appropriate places. So it looks like a complicated program, but 99% or 95% of it is written automatically for you. For example, that interactive driver session, you input the F1, A1, so forth, and that ends up here. So either way, you end up with a Fortran program, and you run that using run PD2D, which compiles and links to the PD2D library and executes it. Okay, well, a lot of students today will say, uh-oh, I'm not familiar with Fortran. I use other languages, and I'm not familiar with Fortran. That's going to slow me down. Well, for simple problems, it won't slow you down, because for either the GUI or the interactive driver, basically the only Fortran you need to know are simple Fortran expressions using star for times and parentheses and so forth. Pretty similar to MATLAB, except a couple of major differences. If you're familiar with MATLAB, Fortran is not case sensitive, so uppercase U is the same as lowercase u, whereas it's case sensitive MATLAB. And the exponentiation, like x cubed, would be x star star 3 in Fortran. Those are the two main differences. Otherwise, they're pretty similar. So for simple problems like the first few we'll do, you really don't need to know anything about Fortran except Fortran expressions, and those are so similar to MATLAB it'll be pretty easy. But you are going to have to learn a little bit of Fortran. Now, for more complicated problems, you are going to have to do a little bit of Fortran programming, but that's what gives it the flexibility. For example, if you're F1 here in the partial differential equation, suppose that was a complicated function that couldn't be defined in a simple expression. Suppose it had to go read a file and interpolate, for example. Well, then you're going to have to write a Fortran function that goes and reads the file and interpolates. So for more sophisticated problems, you will have to do a little bit of Fortran programming, but not much. In the last section of chapter I, chapter 0, gives you some programming hints, including some hints on Fortran, and gives you some examples, help you with the more difficult problems. One thing you have to be particularly careful of with Fortran is precision. MATLAB, everything's double precision. You don't have to worry about that. Fortran, you'll normally want to use double precision. It's hardly ever a good idea to use single precision, which means you don't have to worry about this unless you write your own functions like this, in which case you need to make sure everything is at least the arguments and the function themselves are double precision, otherwise you'll get an error without warning. So there are some examples in the last section using for, as I said, for example, this is x square x star star 2. That's different than MATLAB and most languages, and not case sensitive, so it doesn't matter whether that's uppercase T or not. This implicit double precision is a good thing to put at the beginning of every program. That makes everything except variables that start with I, J, K, L, M, and N. Everything else, which is normally real in Fortran, will be double precision then, so that's an important statement. Actually, these two functions I just showed you, you're going to be using those in your one of your first homework problems. So you need to read through this if you're not familiar with Fortran, maybe even if you are. And finally, we skipped the section on accuracy in Chapter I. PD2D uses high-order elements, which means high-order accuracy. The Galerkin method in 1D and 2D uses up to fourth-degree elements. And as you know from 5343, if you're using polynomials of degree 4, unless you do something stupid, which PD2D doesn't usually, you should get order h to the fifth accuracy. So that's much better than finding differences, which is order h squared normally, and not even that if you have a non-uniform grid. But PD2D for a general curved region, like this is for this problem here, it's using the Galerkin method. It's got a curved boundary. The inner boundary is a circle, the outer boundary is an ellipse. And using fourth order elements, you get h to the fifth accuracy, where h is the diameter of the triangles, average triangle. And you can see the error is extremely small here. Even with 4,000 triangles, 10 to the minus ninth relative error in less than 1 second CPU time. Then the collocation method always uses, for 1D, 2D, or 3D problems, uses cubic elements, so it's order h to the fourth. And it also gets high accuracy. So basically PD2D uses higher order finite element methods, which gives you high order accuracy even when you have curved region. And one more thing, this section 4 discusses the linear system solvers, which is critical for the efficiency of any of these methods, especially 2D and 3D problems mainly. PD2D gives you several options to solve the linear systems, and that's where most of the computer time and memory is spent for 2D and 3D problems. And it has some direct, sparse direct solvers and iterative methods. The sparse direct solvers are the workhorses. Those are the ones you should normally choose. It also has some parallel solvers which will run efficiently on a multiprocessor machine, which you're going to be doing some of your problems on or most of your problems on the multiprocessor machine, so you may use this also.